Module 18 Post Hoc Tests. So today we will discuss about the Tukey's HSD, that is honestly signified differences. I told you the problem with ANOVA is that ANOVA will just brings you overall group is, the difference between the groups are significant or not. So if you're comparing 10 groups, so ANOVA result will just say that our 10 group means differing or do not differ. So if it say yes, it differs, so that means that it could be because of only one of the group has a mean which is differing from the rest of the group means, or 2 has different from the rest of the 8 groups, right? So those intricacies are not known if you are doing the just normal ANOVA. So usually ANOVA test is always or invariably followed by post tests or post hoc test, especially Tukey's HSD. So what is that? What is the problem with this kind of thing instead of simply going for multiple t-test? I told you in the beginning of ANOVA, people will always ask, why not? Why do you have to go for an ANOVA? You can simply go for multiple t-tests. The problem is that if you do this kind of multiple t-test, the problem is called multiple comparison. That's a very, very big problem throughout the statistics. If you do a lot of tests, then finding the false positive is dramatically increased. So just by randomness alone, you will get some positive value if you do a lot of tests. So that is not recommended at all. So you should never do this multiple comparison. But there is a workaround. The workaround is that this p-value you can adjust it. Adjust for doing this multiple comparison. So one such method is known as Bonferroni Adjustment. So let us say in our earlier example, the heavy metals, there are 6 heavy metals. There are 4 heavy metals, but if you look at that pair-wise comparison, how many pairs are there? For example, uranium, lead, arsenic and mercury. These 4 are the heavy metal. So uranium versus lead is paired t-test I can do. Then uranium versus arsenic is another paired test I can do. Uranium versus mercury is the third one. Then lead versus arsenic is the fourth one. Likewise, there are 6. There are 4 number and you are taking 2 at a time. So it's basically a combination problem. NCR is equal to n factorial divided by n minus r factorial multiplied by r factorial. So factorial is with an exclamation symbol, n factorial, n exclamation. That means that if n is 6, n factorial is 6 multiplied by 4, 5 multiplied by 4 all the way to 1. So that is the meaning of this factorial. I will explain more about the factorial and permutation and combination in the module when we discuss about the the permutation and combinations. So here if you do this NCR is n factorial by n minus r factorial and r factorial, and here r is 2 because it's a it's a paired test that we are doing it, and n is of course it is 4. So 4 factorial divided by 4 minus 2 factorial multiplied by 2 factorial is equal to 6. So that is why you would need 6 t-tests. So if you do not adjust it, then the p-value, very low p-value, whatever the p-value that you are going to get will have, there is a huge chance that the low p-value is because of the false positive or type 1 error. One such adjustment is called Bonferroni Adjustment, named after the Italian mathematician. So it's very simple. If you are comparing totally, in this case we are comparing with 6 different paired t-tests, unpaired t-tests in fact. So in that case 6 is the total number of comparisons. So unadjusted p-value you are multiplying with total number of comparison. So that is 6. So each p-value you are multiplying with 6, and then you will get that particular adjusted p-value or Bonferroni adjusted p-value. For example, a t-test comparison of the mean uranium versus mean of arsenic, that is 61.025 with 89.067 yields an unadjusted p-value, that is two-tailed p-value of course, is 0.0006. Now this is unadjusted. So to adjust it with Bonferroni, all you have to do is this p-value should be multiplied with total number of t-tests that we are doing, or total number of comparisons that we are doing, that is 6. So if you multiply it by 6, that the adjusted p-value is 0.0036. So had your significance level been 0.001, so in that case then this is more than that p value, so it is actually not significant. But had your significant level been 0.05, yes, it is still significant, the result. But most of the statisticians agree that most robust way to avoid this multiple comparison is that the problem with the false positive is something called Tukey's HSD. So the formula for Tukey's HSD, as you can see, is very simple. So it's basically, it calculates the confidence interval of the difference between two sample means. We have already seen how to calculate this in the t-test, right? So SCM of the difference, and then we are actually using this standard error of the differences with the differences between the group means. So M1 minus M2 divided by standard error of the difference, that is used for the t ratio. So in this case, it's a confidence interval of the difference in the group means is what is being calculated. So first you have to calculate the difference between the two group means. So that is xi minus xj, plus or minus. So that is the formula here is q. So there is something called a constant q for Tukey's HSD. Q given alpha, R and degree of freedom. So R is number of groups. So K, sometimes it's called K, number of groups. Then alpha is, it is significance level, and degree of freedom. So given these three values, alpha and R and degree of freedom, you can look up the Q in the Q table, or on using an online calculator, you can check out what this Q, the constant Q is. Multiplied by square root of MS within, that is MSW, divided by 2, multiplied by 1 by Ni plus 1 by Nj. So two groups, what are the group sizes? So this is the formula for Tukey's HSD. As you can see, after plus or minus, all those is something called width of the confidence interval, 95% confidence interval. So this width plus or minus. So basically the Tukey's HSD calculates the confidence interval of the difference of the sample mean. And you can plot that in a nice way, graphically. So you can see that is it actually the null hypothesis of no difference is part of it or not. So no difference, null hypothesis is 0. That means group means are equal, or mean of the first group minus mean of the second group is equal to 0. So if this Tukey's HSD, the confidence interval includes that null hypothesis of 0, that means the p-value must be larger than 0.05, and if it doesn't include, then p-value must be lower than 0.05, our chosen significance level. So Tukey's HSD returns a corrected 95% CI of the difference between the two group means. Uncorrected way to do this same thing is simple t-test. So as you see that in this or the simple confidence interval, if you calculate the simple confidence interval, that is basically SCM of the difference multiplied by the t constant. So that is not adjusted, but in this case it is really adjusted with, because the Q, the constant Q is also depends upon R is total number of groups, total number of comparisons that you are going to do, and MS within also depends upon the overall variance, and within the group variance, all these are very important for MS within, that we discussed that in the last section of the same module. So let us do this work for the lead versus uranium. So to compare the means of lead versus uranium, so our the first two groups of the last ANOVA problem. So we need first to calculate the difference between their respective group means. So mean for lead is 78.13 and mean for the uranium is 61.03. So the difference is 17.1. So now 17.1 plus minus the 95% confidence interval. So that we will have to calculate using the Tukey's HSD formula. So next step is to calculate the width of the 95% confidence interval. So given that significance level is 0.05. So to calculate, we need to know following information. First is MS within, then degree of freedom within, then lead, what is the sample size, the N of the lead, then N of the uranium, then we need alpha, that we already know it's 0.05, then R is total number of groups that we include, that is 4, and then the Q. So you need to have 7 information to plug into this equation and then to get this thing. So MS within is basically 14.753. We have already calculated in the ANOVA. When we did the ANOVA, we have already know its MS within is 14.751, while degree of freedom within is 11. Then total number in the lead group is 4, while uranium group is also 4. Alpha is 0.05 and R is 4. So R is 4 because of 4 groups. So plugging into this value, the same equation, it's direct, you can simply solve it, then basically you will get the answer for that particular thing. So now, but where is the Q? How do you calculate the Q? So Q, you have to look up the appropriate Q table with alpha is equal to 0.05, that is significance level is 0.05, R is 4, the 4 groups, and degree of freedom within is 11. So degree of freedom, R and sigma, significance level, the alpha. So usually the Q tables are not given in statistics books because it is quite complicated. It's very tricky to calculate the Q. So you can simply go to an online calculator like the one which I linked. So in this calculator you just have to put these 3 values, and then Q at 0.05 significance will be given and Q at 0.01 significance will be given. So all you have to put is the degree of freedom and what is that? It's basically the R. R means the total number of groups. So if you put it, you will be getting the K value. So lead versus uranium, going back to the same problem. Here it is Q at alpha 0.05 is 4.27. So now we have that missing value as well. So if you plug into the same equation, if you solve it, it's going to be 8.2 is the width of the confidence interval. That is what we are going to get. So that is basically the width of the confidence interval after Tukey's HST correction. So it extends both sides of the difference between the means. So the difference between the group means is 17.1. So 95% confidence interval for this difference is 17.1 minus 8.2 to 17.1 plus 8.2. So if it is the mean is in the center, plus or minus, so it's basically an error bar, like standard deviation error bar or 95% confidence interval error bar. So basically it is 8.9 to 25.3 is the confidence interval, 8.9 to 25.3. Now the question is that, does this interval includes your null hypothesis? What was your null hypothesis, by the way? It is 0, because the 2 group means are 0. The difference between the 2 group means are 0. Group mean 1 is equal to group mean 2. So does this range include 0? It doesn't, right? 8.9 to 25.3 do not include 0. So only such confidence interval where there is minus and plus, -5 to +5 for example, includes 0. But in this case there is no 0 in it. So what does that mean? Then that means that p value must be lesser than 0.05 and the results are statistically significant. That is the that is how you can infer from the Tukey's HST test. So we can perform the same pairwise computation of 95% CI for all the 6 combination of the group means as well, to find how many of these combinations return statistically significant differences. So confidence interval of the difference between the means tell us whether the p value is significant at our chosen significance level. Some software like GraphPad Prism also returns the exact p value called multiplicity adjusted p value. So that had been adjusted for the multiple comparison. So the p value is additional information. So this is a summary table. If you do the same thing using GraphPad Prism, so you will know that is it significant or not, along with the p value. So if it's borderline significance, you can spot it by looking at the exact p value. We can also plot the same information graphically, in a very simple error bars description, as you can see in the screen. So this is 95% confidence interval, that is adjusted by the Tukey's HST method. So you can see there are four groups while there are 6 pairwise comparisons that we did. The first is mercury versus uranium and all the way to the lead versus arsenic, the last one. So the first is mercury versus uranium. You can see that the dot represent the difference between the group means, and then plus or minus the error bar, the left side and right side. These error bars are equidistant from the center. So as you know, it's plus and minus, and this one is nothing but 95% confidence interval, while in this one you can see in the middle there is a dotted line. So the dashed line represents our null hypothesis of no difference, so that is 0. So does the difference, the 95% confidence interval, include that null hypothesis or not? That is the question. In the case of mercury versus uranium, the first one, no. Second one is arsenic versus uranium, also no. Third one, arsenic versus mercury, yes. The confidence interval, that is the error bar, also include the dashed line. So that means that arsenic versus mercury, the differences are not statistically significant. The fourth one is lead versus uranium. Again, it doesn't include the null hypothesis. The fifth one is lead versus mercury, yes. It touches the dashed line of null hypothesis passed through the 95% confidence interval. So that means that lead versus mercury is also not significantly different. Now the last one, the sixth one is lead versus arsenic. No, still it doesn't include the null hypothesis. So that means that the differences in the group means are significant in that case. So usually if you read the paper, the 95% CI is plotted on the mean directly. So in this case you can see that here it is mean plus or minus 95% confidence interval. So as you can see that in this case it is basically Tukey's multiplicity adjusted p-value. It's not just normal normal confidence intervals as well here. So in this case there are different numbers here, right? Conventionally the option is that if the two error bars have got the same letter, for example the first and second one is B while first is A, while third one is A and B. So the third one is not significantly different from A, that is the meaning, the first one, and the third one is also not significantly differing from the second one because they both share the letter B. So that is the meaning. So all these are inferred from the Tukey's HST. And the fourth one is basically C. That means that it's significantly different from first, second and third group. So that is the inference of this 95% CI of the mean. It is the normal 95% of the mean, but these letters, you infer these letters after doing a post hoc test like Tukey's HST test. So in this thing it's clearly mentioned that A, B, those letters are inferred from Tukey's HST test. And also you can see that do the error bar, that is basically 95% CI, overlap or not overlap. That is also very interesting. So A and B do not overlap, so therefore they are significantly different. So you don't even need to do any other test. You can conclude straight way. But because there are a lot of comparison there, it's always better to do a formal post hoc test like Tukey's HST. So this is another data from a paper which we picked up. So as you can see that here also the same thing, that the error bars are nothing but 95% CI, but the letters on this error bar. So error bar need not be 95% CI as well. It can be standard deviation or standard error of the mean, but these letters are some kind of post hoc test. So usually it is Tukey's HST. So here is another another of the paper. So by looking at that, these letters signifies is the differences are significant or not using Tukey's HST. Please remember that it is possible that the one-way ANOVA returns a p-value which is lesser than 0.05, that means it's significant, but none of the pair of the means differences are significant. How is it possible? Yes, it is possible. Overall groups, if you have like 5 groups, the mean of the overall 5 groups is significant, the differences are significant, but pairwise not significant at all. That is one possibility. So it is not unusual as well. It's also possible that the ANOVA returns a p-value more than 0.05. That means there are not significant differences between the group means, yet some of the difference between the group means are significant. So because of the second possibility, even if the ANOVA says there is no significance, still you can perform Tukey's HSD to see how the group means are performing. So maybe some pairs are significant or not. And Tukey's HSD is just one type of post hoc test, but there are several others as well, or these kind of post tests. One is called Dunnett's test. It's highly useful to compare the multiple groups with a group defined as a control group. So if you have a control group and you're comparing this control group with different groups or test groups. So in that case, so especially in the biology, so usually we have something called control, a negative control or a positive control, and then you're comparing this control with 1, 2, 3, 4 test samples. So in that case, Dunnett's test is most appropriate rather than going for simple Tukey's HSD. Chaffee's test is to compare the contrasting sets of the values of the groups. For example, groups A, B, C compared with versus group D and E. So if you have like contrasting groups, for example, cases and control, for example, these are contrasting. So you can actually compare that with the Chaffee's test. Another test is called Holmes test. So it returns adjusted p-value, but there is no confidence interval for the Holmes test. So there is a there is a con. It's always better if it returns a confidence interval so that we can actually see that whether it's significant or not. So it returns only a p-value. So if you want to calculate this ANOVA with Tukey's HSD, every calculation through online, so there is one such calculator. I mean, there are several calculators. The one which I recommend is already put up in the web links of the course or in this PPT also you can check it. So the same thing that the lead the problem, the 6 comparison, we can do that in that calculator. So it also includes the results of the other multiple comparison test, including Bonferroni test, Chaffee's test and Holmes test. So you can see that everything, but remember, just by Chaffee's test says that the p-value is less while all other tests are saying p-value is high, never go for that. So there should be a rationale to choose one test over other. And if you simply do n number of tests and choose the one which shows the lowest p-value, that is wrong. That p-value or that conclusion is most probably because of the false positive or type 1 error. Also note that even though the ANOVA returns an overall p-value which is higher than 0.05 and the differences are not significant, the results of multiple comparisons like Tukey's HSD, Bonferroni test and Dunnett's test are still valid. So it is not saying that it is invalid. If you get a p-value higher than 0.05 in ANOVA, you should be stopping your test. That is incorrect. You can still do and the inferences are still valid in the post tests. So this is the how Tukey's HSD in tabular format in the GraphPad Prism. This is for the pH example, the microbiology example which I presented in earlier section of the same module. So you can see that there is basically even the p-values are also given in this and statistical significance is also written for this thing. And the same result in graphical representation also you can see that. So in this case, the first value is only comes, the null hypothesis of the dashed line is intersecting the 95% confidence interval of the difference between the group means only in the first case. So second and third is statistically significant while the first is not. So let this be of one of the assignment. You can turn in through group discussion. You can discuss it amongst yourself as well as me. I can contribute into the discussion. The assignment is that compare the means of the two groups using appropriate test of significance. So are they significantly different or not? So group 1 values are given, group 2 values are there. So how do you compare these groups using the appropriate statistical test? So which test you will choose, then the rationale of that test, and then how will you interpret the results. Second assignment is that compare the means of the 3 groups using appropriate test of the significance. Are they significantly different? Also perform appropriate post test for the multiple comparison. Present the data graphically. So we have now 3 groups, group 1, group 2, group 3, and which test will you use to compare the group means are significantly different or not. And then you can also do a post test like Tukey's HSD and present the data in a graphical manner. So in summary, performing multiple t-tests increases the probability of finding an incorrect significance, that is nothing but false positive or type 1 error. To correct, you should multiply the p-values of each of the pairwise comparison by the number of comparison. If you do like 6 comparisons, then each p-value should be multiplied with the 6. So that adjustment is known as Bonferroni adjustment. Tukey's HSD is a single step multiple comparison procedure and statistical test, far more advantageous than the Bonferroni adjustment. It returns a corrected 95% CI of the difference between the 2 groups or 2 means. So this is the CI of the difference between the means. It's not on the mean, it's not performed on the mean, but it's performed on the difference between the 2 group means. If more than 2 factors are included, 2-way ANOVA should be performed, not just 1-way ANOVA. Thank you for listening to this module, and I hope you're enjoying. And this comes to the end of the 7th week, and let us sum up what we have learned in the 7th week. Thank you.